Good morning, guys.
Good morning.
Good morning.
Morning.
Good morning. Okay, guys. Now, any questions? Nope. Okay. Now, what I would like you guys to do is come back to page. How are you doing this? Page 243. And what we mainly are going to be talking about is just, okay, two elements of digital scan, or we can say, okay, data. Okay. Now, one is going to be, is okay, what we'll call a pixel. The other is going to be, is okay, what we'll call a bit. Yeah, okay. And these are mainly as okay two components that actually is okay makes up primarily as okay digital data and digital images. Okay. So we will be talking a little bit about these two components here. Now, when we look at the word pixel, it is actually made up of or derived from two words. The word pix actually is okay comes from pict, which is derived from picture. Okay, where it means that's okay, what's going to be a picture? Yes, okay, that's just going to be an image, or what we in chapter 13 refer to as a frame. Is that clear?
Yeah.
Good. The word L or EL actually is okay, is derived from element. Okay. Now, by this element, we don't mean things like okay, sodium, chloride, hydrogen, carbon, oxygen, and things like that. Okay. But like these elements were just okay, the basic building block of all materials that we see around us and don't see around us. Likewise, the pixel that's going to be as okay, the basic building block of a picture. So if we say that, okay, yes, if we have a whole image, what this image here is going to be, is going to just okay, be built up by bigger or smaller building blocks. Each of these building blocks here is going to be called a pixel. Did you guys get that?
Yes.
Okay. So pixel, what is a pixel? We can say, okay, literally, yes, okay, is the building block of a image. Most likely, yes, okay, when we talk about pixels, that's going to be, yes, okay, a digital image. Yeah, okay. And that's why nowadays, that's okay, for instance, it's okay when you buy a camera. Or even if you don't buy a camera, even if you look at the camera of your cell phones. Okay, it may say it's okay, this cell phone here is okay, it comes with a camera that has this many megapixels. Okay, where the mega mean, yes, okay, will just be million. And pixels, well, okay, yes, those basic amounts or those basic building blocks. Did you get that? Okay, and of course, that's okay, the kind of images that you, yes, okay, take by a cell phone, which is a digital medium, is going to be, yes, okay, a digital image. So that's why it's okay. The cameras are now, it's okay. The camera quality or the picture quality that they may be taken is going to, yes, okay, be expressed in terms of megapixels, gigapixels, whatsoever. Okay. I remember my first digital camera that I bought many years ago. Not in a phone. That was before, yes, okay, you had cameras, yes, okay, coming with the cell phone. It was, okay, yes, 3 kilopixels. So kilo is just not going to be millions, but rather just 1,000 pixels. Okay. But yes, okay. So that was pretty much okay. That's what they had back then. But I will say, yes, okay. Technology has evolved. Clear? Okay. Now, guys, on a digital image, on an image or on a scan or on a frame, what is going to, yes, okay, determine the, we can say, it's okay, number of pixels per frame? Okay, oh, let's say it's okay, what's going to determine the number of pixels? That is mainly as okay going to be as okay described by as okay what we call pixel density. Now pixel, what was pixel? That's okay. That basic unit of a digital image. What did we mean by density? Whenever you say density, what should be the first thing that comes to your mind? That's going to mainly express, okay, explain how closely, that's okay, the thing that we're referring to is packed together, or how loosely they are packed together. Okay, so that's mainly going to be as okay, we can say it's okay, the concentration of, okay, that's okay, or pixels, okay. And of course, that's okay, that's going to mean that's okay, be per unit of area of distance. So here is okay, that is going to be as okay, expressed in per inch. Yeah, okay. That is going to be expressed as per inch. So a pixel density is going to be as okay, the number of pixels. Okay, the number of pixels in 1 inch of your digital image. Well, let's say it's okay, inch square. we call mainly as okay what a pixel then will be. Is going to be something like this. Okay. Okay. But if we say that, okay, as if we take, for instance, okay, an image. Let's take this, okay, an image. Okay. And if we take 1 square inch of this image, let's say it's okay, this is 1 square inch of your image. Okay. Now the pixel density mainly is okay, just going to be how many pixels did we have in this 1 square inch of your image. That is going to become your pixel density. Did you guys get that?
Yeah.
Yeah, okay. But this pixel density, guys, this whole pixel density here is going to be equal to, we can say it's okay. Pixel density is going to be equal to your line density. Okay. So what actually is okay is going to determine your pixel density is going to be as okay the number of pulses. That in this case is okay will be per frame. Did you guys get that? Now what we mainly can say then is that greater, let's take it to another picture, another slide, sorry. If we say it's okay, pixel density. What that will lead to is, how is that we will relate that to? Yes, okay, we will also, yes, okay, go on and relate that to, yes, okay, pixel size. And this pixel size, yes, okay, versus pixel density is going to be important once we start talking magnification. Okay. But then we can actually say it's okay that okay, yes, it will affect us, okay, what we will call resolution, which will be yes, okay, a spatial resolution. So if we had a great pixel density, which will mean that okay, yes, we will have a great number of pixels per square inch. That will be a great pixel density. That will mainly as okay be equal to, or mainly as okay cause that we will have a lower pixel density. Oh, sorry. Okay. So no. That we actually will have a smaller pixel size. And due to that smaller pixel size, that we actually call, or we can say, okay, a greater number of pixels or greater pixel density actually will lead to we have, okay, as what we can call a good spatial resolution. Okay, So your spatial resolution, guys, please, 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 that spatial resolution is going to mainly as okay be determined by your pixel density. Yeah, okay. Did that make sense? Whereas, okay, if we go oppositely and say it's okay, a lower pixel density, that's mainly going to mean that we have a lesser number of pixels per square inch. So, okay, since there's going to be as okay, lesser number of pixels in 1 square inch, that will mainly cause that we will have a greater pixel size. Clear? Okay. And I lose, yes, okay, that greater pixel size, which causes the pixel density to be lesser, is going to lead to that we will have a bad or poor spatial resolution. So from now on, yes, okay, when we use the word spatial resolution, what would that actually is okay account for? That either yes, okay, the number of pixels per square inch is going to determine that, or the size of your pixel. Okay, but if you, for instance, say that, okay, let's do it this way and say it's okay, we have 1 square inch area. Yeah, okay. Now, if you, for instance, say that, okay, yes, if that was going to be, it's okay, a great number of pixels. Within that square inch. That was mainly because, yes, okay, if we looked at it, yes, okay, we will have a small pixel size. And that small pixel size gives us, okay, as a greater pixel density, which will cause, okay, this image here will have a good spatial resolution. Whereas on the other hand, if we said, well, okay, yes, same square inch of the image, but we had a big pixel size. And what we see here is, okay, in 1 square inch, we only had is, okay, 4 pixels. Where we can say is, okay, maybe here we can say, okay, 20, 25 or whatever. Clear? Okay. Clear? Okay. But due to this great pixel size here, oh, that's okay, the lower pixel density per square inch, yes, okay, we are going to end up with a bad or poor Excel or spatial resolution. Yeah, okay. But what causes, yes, okay, the pixel numbers to be great here and what causes the pixel number to be low here is mainly because here we have greater number of pulses. Whereas here is okay, we will have a lower number of pulses. Did you guys get that?
Yes.
Okay. Now, guys, have any of you ever seen a TV program where they, for instance, okay, well, I won't use the word fade out because that fading out can be as okay understood in another way. But actually, it's okay. They grade the picture quality by as okay. What they do is they apply a filter. But instead of as okay, seeing as okay a clear picture of the person who is talking, that picture mainly as okay just develops into big boxes. Okay, probably not something that we should have discussed, but have any of you ever seen Jerry Springer? He's dead now. Okay. And when somebody is okay, all of a sudden, yes, okay, say, well, I'm here to, yes, okay, collect a free shirt. What would they do? Okay, whatever they did, or what the cameraman or, yes, okay, the editors would do was they would edit that image by, yes, okay, turning it into, yes, okay, big blocks so that you couldn't see the actual details, right? Okay, what that filter did, it made, yes, okay, just degraded your spatial resolution by increasing the pixel size. Let's do it this way, guys. For instance, okay, if this here is okay was an image. And let's say it's okay, we got that because we had a high pixel density because we had a low or small pixel size. Clear? But if I just do the opposite here, it's okay, reduce the pixel density mainly as okay by increasing the pixel size. Okay. This thing here is okay that we had drawn this image here. May just appear like this. Or it's actually going to be as okay rather than being round like this. More just like big boxes. Okay. Now, yes, okay. Of course, that's going to be as okay a filter, but what that filter does actually is okay, increases the size of each pixel. And by doing so, causes that, okay, yes, the pixel density is decreased. And as the pixel density decreases, well, okay, yes, that will lead to, yes, okay, a degraded spatial resolution. Any questions?
No.
Let's see. Can you guys see this fellow here? Let's just. Okay. So this is pretty much okay. That's if we just further enlarge it. This is what the mainly is okay. I've done to yes, okay, an image where we mainly consider okay as where we mainly consider okay as this here, or even something like this is 1 of 1 pixel. Or even if you look at this black dot here, what is this? That is 1 pixel. Clear? Okay. So what they mainly did in this picture here, they mainly is okay, caused each pixel size or the size of each pixel to increase. Okay, so each pixel you can see is okay, mainly as okay, it just looks like a big spot or bigger spot or bigger, smaller box. Clear? Okay. Where you can say, okay, now this one is okay, this could be 1 inch, another 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 inch of your picture here. Okay, so you could say, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, for instance. But then your pixel density was going to be, okay, how many pixels do we have in, okay, as a square area of 1 square inch. Okay, or we can say, okay, here, for instance, this was 1 square inch of a picture. The number of pixels that you count here was going to be, okay, your pixel density. That is going to be less in this case here because of the greater size. Clear? Did that make sense?
Yep.
Okay. Just if you go to just okay a donut store and say, well, okay, I want, that's okay. They have a donut box. And they say, well, okay, this donut box is going to cost you, okay, $20. They have a fixed price. Now it's up to you whether you want to fit small size donuts into it, or whether you want to go with, okay, yes, the big size donuts. Right, okay. So of course, that's okay. You fill this box up with small donuts, that's going to be as okay. A lot of donuts that will fit in. Okay, and in that case, you can mean it says, okay, due to a greater, I guess, okay, a smaller size of the donut, are able to just, okay, fit in a greater number of donuts in, okay, as a box, which was, okay, as a 1 square inch. Whereas, okay, if I chose big donuts, which are going to be, as okay, a big pixel, I will only be able to just, okay, fit in, what you want to call it, a lesser number of pixels or lesser number of donuts into that box. Okay. But, and that's why it's okay, axial resolution and spatial resolution pretty much okay makes the same meaning here because okay, what is going to cause or determine your pixel density is going to be as okay, the number of pulses. Did that make sense? Okay. Clear? Okay. So the number of pulses. But if you look at your book, in figure 15.5, a same picture of the flower that you see in picture B, just as okay, with bigger pixels. So A, what do we have? Bigger size pixels. Clear, okay, where you don't really can see as okay, well, you can see as okay, some yellow boxes, some purple boxes, some light blue boxes, some green boxes, but that's pretty much it. Okay, you can't clearly as okay outline the flowers and not see as okay the good details of the flowers as you can see in picture B, which is higher pixel density due to smaller pixel size, which gives you as okay, obviously as okay, better spatial resolution. Did you guys get that?
Yes.
So A is bad spatial resolution, B is good spatial resolution. Okay, all dependent upon as okay, the pixel size, which is inversely proportional to the pixel density. Yeah, okay. Or yes, okay, the next time you watch a program where okay, something is being out, yes, okay. If it is okay, if that appears in bigger boxes, what they mean is okay, just did was increase the pixel size. And by increasing the pixel size, decrease as okay, the spatial resolution. Or in that case, as okay, hide out the identity of the person. Clear? Okay. Any questions? So for now on, guys, spatial density is determined by the pixel density, which is determined by the pixel size. Did you guys get that? Any questions? Nope. Good. Now, have any of you ever done a basic computer course? Not specifically a master's in computer science. Any is okay, computer 101. Good. Because that may help you a little bit. If not, well, okay, yes, I can always try to, yes, okay, do my best to explain it. Well, the next thing is going to be, is okay, what we call a bit. Clear, okay? Now, some of you say, well, okay, yes, we know that. Just wait a little bit. Okay, but yes, okay, here, this bit doesn't mean that little bit. This bit here is, again, yes, okay, an abbreviation. That means, it's okay, going to be used to specify as okay, a form of digital data, to be more specific. Okay, so the bit is again, yes, okay, just like pixel, yes, okay, derived from two words. Binary, digit. Now, what I said yesterday, when we say it's okay, digital data, or let's say, okay, digital data or format of digital data. I mainly say that, okay, yes, digital data is mainly, is okay, just made up of series of zeros and ones. So mainly it's okay because it is mainly it's okay made up of two numbers. That's why we call them binary numbers. Okay. Now those two numbers, they can't be, you can't say that, okay, couldn't it just be 2 and 3? Couldn't it just be 3 and 4? Couldn't it be 7 and 11? Okay, 7 and 9, for instance. No, that is pretty much standard. It's just going to be made up of series of zeros and ones. But mainly because it is made up of these two numbers, or mainly it's okay, just series of as okay, two numbers. That's why they're called binary numbers. Okay, so binary here is bi. Right. That's okay. Here we use the word digit just to make it more digitalized, but it's okay. The digit mainly is okay would mean it's okay a character. Where 1 is a character, 0 is a character. Yeah, okay. So whether you say yes, okay, the T for the bit from the digit, or whether you said, well, okay, yes, the B from binary, and then the it from digit makes up a bit. Okay, so computer data is just going to be as okay. So what were our 2 bits? It was made either 0 or 1. Okay, now each of these here is going to be as okay accounting for 1 bit. Okay, but your computer pretty much okay is not going to read this one here as 0. It's not going to read this one here as 1. Okay, because the next step is mainly going to be that we say is okay if we have a total of 8 bits. 8 bits, that makes up, okay, as a term that most of you will have heard again and again and again, and that's going to be 1 byte. Okay. And don't ask me why 8, why not 10, why not 6? That's not me who determined that. Okay. Okay. So what they mainly said, well, what they mainly is okay, decided that okay, yes, 8 bits is going to make up 1 byte. Now let's say it's okay that we just write 8 bits. Okay. 0, 0, 1, 1, 1, 0, 0. Here. These are 8 bits. Okay. So, yeah, 8 bits. So that actually is okay together equals to 1 byte. Did you guys get that?
Yeah.
Good. Any questions?
No.
Now, what they further said was that if we, for instance, okay, take 2 bytes, or let's do it this way. We can say it's okay, 16 bits, which makes 2 bytes. That is going to be equal to 1 word. So yes, okay. You on your computer may write the word red. Then you type in R-E-D. Okay. But this word right here is okay. The computer is going to read it as 001111 0000 until it's okay. It has 16 bits or 2 bytes, and that's going to read the word red, for instance. Okay. So how is it that your computer works? On your keyboard, you don't see as okay zeros and ones. Otherwise, that would have just been 2 keys on your keyboard, right? Then you had to be able to just okay know how to digitally spell the word red, how to digitally spell the word yellow, blue, purple, green, how to digitally spell your own names, which was just going to be as okay a long or a shorter series of zeros and ones, following or coming in whatsoever crazy sequence. Okay. Now you open a Word document, for instance. Let's keep it pure to the computer, no email. Okay. You type the letter P-L-O or P-L-E-A-S-E. Write the word please. Clear? Okay. What your computer does is, well, okay, convert that into, yes, okay, digital words. But you see it on your screen as P-L-E-S-E-E. Okay. Now you may write a document, save it. Clear? Okay. Now that is going to be saved in a digital format. Okay. Now, if your computer, yes, okay, is working properly, you can open that document up again. And okay, what you ideally is okay, would like to see is okay, yes, whatever you had typed. Did that make sense? That's because, yes, okay, your software of the computer or the program, as we may call it, in which you open it, is able to just okay convert it from that digital form into a analog format, so that you actually can see the words as you have, or the document as you have written it. Did that make sense? Now, God forbid that if your computer, for instance, okay, was attacked by a virus, what is that virus may tend to do? Infiltrate or penetrate or yes, okay, infest or infect your softwares. And when you watch, yes, okay, open that document, you don't see the nice note or essay or letter that you wrote, but you may see as okay, a lot of okay, yes, figures, smileys, letters that you can't read written in okay, yes. And why that? Mainly because okay, now that program has been corrupted. So it's not going to be able to just okay convert from a digital format back into an analog format. Okay. You may try to sit down there as okay, try to decode okay as what 6 skulls and okay, yes, followed by 7 sevens and an O means. Because that's not what I wrote. Clear? Okay. So that's how it works, or that's how it may not tend to work. Okay. But if next time, yes, okay, you can do it, okay, during your break. Go into, yes, okay, where you save your files. And the next thing you may see next to the file is, okay, yes, of course, it has a file name. It may be, yes, okay, a file format. Was this a Word document? Was this a PDF file? Is this a Excel sheet? Is this a picture? And then you see the word size. Okay, now nowadays, yes, okay, usual files comes in, okay, as things such as kilobytes or KB. Now, what does that KB stands for? That stands for kilobytes. A kilo is going to be 1,000 byte, 8 bits. Okay, so what does that tell you? How much digital data, or how much space, for instance, okay, on a hard disk or on your computer is it that this space or this program here is occupying in terms of, yes, okay, digital memory. Okay, so that becomes, yes, okay, the size of your file. Whether it's a document, whether it was a picture, whether it was this, whether it was that. Did you guys get that? So bit still is, yes, okay, the single binary digit. There's 8 bits makes up a byte. And 2 bytes or 16 bits makes up a word. Did you guys get that?
Yes.
Okay. Now the next thing. Okay. Because, okay, of course, yes, okay, we're not going to be talking about, yes, okay, written Word documents and so on. So our main emphasis is pictures. Or we can say it's okay, images. Is that clear? Okay. So again, guys, if we said that, for instance, okay, this here is okay, was 1 pixel. This here is okay, was 1 pixel. Now, the bits per pixel is going to, yes, okay, determine the contrast. Yeah, okay. And it's still going to be, yes, okay, the number of bits that we have per pixel that will determine the contrast, which then, okay, yes, will determine, yes, okay, our contrast resolution. Did that make sense? But what was bits? Generally, yes, okay, in computer terms, we always, okay, we refer to that as, okay, as the basic of computer data or a binary digit. Okay, which could either be, as okay, be 1 or 0. Because, okay, if I wrote, let's say, it's okay, 1 byte, each of these numbers here, or each 0 and each 1 accounts for 1 bit. Is that clear? So if in this pixel here, in this pixel here, 1 pixel, we only had what we say is okay, 1 bit. That mainly means that okay, this pixel here is okay, only could have 2 possible colors where one was black and one was white. Now, what would that lead to? We mainly could say it's okay, or we actually said, okay, this was okay at the greatest contrast. Yeah, okay, because we only had 2 shades. Or we are only able to just, okay, have 2 possible shades, black and white. And due to just, okay, the greatest contrast, that was going to cause that, okay, as we will have the poorest contrast resolution. Now, guys, if we only had 1 bit, which only could give us as, okay, these 2 shades here. That's why it's okay, a picture with only 1 bit per pixel, which only as okay can give us okay black or white to each pixel. That is going to be referred to as being bistable. So bistable, guys, is the highest contrast and is going to give you, yes, okay, the poorest contrast resolution of an image. Because if these were the 2 only colors that I gave you to work with, and say, well, okay, yes, now make a Mona Lisa. You say, well, okay, but what about the lighter shades of gray? Or what about the darker shades of gray? I say, no way. We'll say, no, yes, okay, lighter or darker shades of gray, only black and white. Okay, so since you can't put those shades into your image, due to it's okay that you only has okay can work with the 2 extreme contrasts, you will end up with a poor contrast resolution. Okay, but the note to take away is that lesser number of bits per pixel. The lesser number of bits per pixel is going to give you, yes, okay, at the greater contrast. The greater the contrast, the poorer the contrast resolution. Did you guys get that? Whereas, okay, on the other hand, if you, for instance, say, as okay, we have, okay, as a similar pixel, but if you, for instance, okay, in this pixel is okay, puts, let's say, as okay, 2 bits. That may actually, yes, okay, allow us to have up to, yes, okay, 4 shades. Yeah, because it's okay, one is still going to be black. One may still be, yes, okay, white. But when we can say, okay, we may have, okay, it's a dark gray. And for instance, okay, a light gray. Did that make sense? Okay, where we then can say is, okay, if we compare black to dark gray to light gray, and light gray to white, is okay, we will have, okay, as a lower contrast. Or we can just say it's okay, a low contrast. Which mainly is okay, give us okay as a good contrast resolution. Did you guys get that? And oh, yes, okay, if we, for instance, okay, see that we have the same pixel, same size here, please keep in mind, guys, your pixel size does not apply. Your pixel size does not apply to your contrast resolution. That is wholly and solely going to be determined how many bits do we have per pixel. But we, for instance, say it's okay, what if we had 4 bits? Now 4 bits, guys, is actually it's okay going to give you it's okay up to 16 sheets. Very still can say it's okay, one will still be black, one will it's okay still be white. But as what we mainly can say here is okay, instead of just having 2 shades of gray between black and white, we actually have 14 different shades. But the total number of shades or colors that we may have I have available here is going to be 16. And that's going to call that that's going to be a lesser contrast. Or from these 3 examples, we can say the lowest contrast. Where this is going to give us an image with the best contrast resolution amongst these 3 here. Okay, but what determines whether we had the poorest contrast resolution, a better contrast resolution, or the best contrast resolution is going to be the number of bits per each pixel. Did you guys get that? So what we straight forward or straight ahead can say is low number of bits per pixel is going to give us a poor contrast resolution. Whereas, a high number of bits per pixel is going to give us a good contrast resolution. But what this low number of bits per pixel that led to us a poor contrast resolution gives us as a great contrast. Whereas the greater the number of pixels or bits per pixel, which gives us as a good contrast resolution, is going to give us a low contrast. Okay, guys. Now you can also translate this number of pixels here into you can say it's okay, your grayscale. Where you mainly will say it's okay, lower number of pixels per, or lower number of bits per pixel, that will give you as okay a small grayscale, which we then can say is okay, can lead to either of these. You can say okay, link it to this, or you can link it to this. Because the smaller your grayscale, the poorer is going to be your contrast resolution. How did you get that smaller grayscale? Because of a lower number of pixels, or bits per pixel. Whereas likewise, that great number of pixels or great number of bits per pixel actually is okay, will also is okay, give you is okay, what we can call is okay, a great grayscale. Which mainly or me, that you actually is okay, also is okay, should be able to link to is okay that there will be a lesser contrast, or is okay that that picture as a whole will have a better contrast resolution. Yeah, okay. But of course, that's okay. We can then say that here, this bistable here is okay. That is the smallest grayscale that you have. Okay. Okay, because you can't have less than 1 bit per pixel. Yeah, okay, by 1 bit, that doesn't mean that, okay, as your bit is made of from digit to 1. No. It could have been 0. But that 1 pixel just has 1 bit, which gives you just, okay, 2 sheets. 2 bits gives you 4 sheets. 4 sheets give you 16. Or 4 bits give you 16. 5 bits give you, okay, 25 sheets, and so on. Okay, guys? So the takeaway point is, what is a pixel? Clear? Okay. Basic building block of your digital image. Made up from the word picture element. From picture comes pix. Just like act, X. Clear? Okay. Your pixel density, numbers of pixels per square inch area. Clear? Okay. Okay. It's going to just, okay, determine your pixel density. Now your pixel density is going to be inversely proportional to the pixel size. That donut box that we talked about earlier, right? Okay. Okay. Yeah, that box and you says, okay, fill it up with munchkins. Now munchkins are smaller than a regular sized donut, right? Did that make sense? Yeah, okay. Did you guys get that? So that pixel density, that is what mainly is okay, will determine, yes, okay, what you call your spatial resolution. Clear? Okay. Now we go on to the next one and say, okay, these were our pixels. Now each pixel may have, yes, okay. Let's say, yes, okay, we fill our box up with munchkins, just to be on the same foot. Yeah, okay. Now these munchkins here only could have two colors. They could either be, yes, okay, black and white. That's because of a low number of bits per pixel. As we may, yes, okay, increase the number of colors that we will be able to, yes, okay, fit into each munchkin. That is going to, yes, okay, is due to, yes, okay, the greater number of bits, which is going to, yes, okay, increase the number of shades that we fit into each bit or pixel, sorry. Okay, but the greater the number of bits per pixel, the greater will be, yes, okay, your grayscale. The greater your grayscale, the better your contrast resolution. Okay, but contrast resolution is only going to be determined by, as okay, the number of bits that you fit into that pixel. Clear? Okay, it is not going to be determined by the pixel size. Your pixel size determines your spatial resolution. Clear? Number of bits per pixel will determine your contrast resolution. So the greater number of bits, greater number of shades or colors can be, as okay, associated to each pixel. Okay, but the greater the number of shades or colors, okay, the greater is going to be your grayscale. The greater your grayscale, yes, okay, the better your contrast resolution. But if you have a greater grayscale versus a smaller grayscale, in a smaller grayscale, there's going to be a greater contrast between the colors or the shades that you have. Whereas, okay, if you have a greater grayscale, there's going to be, as okay, a lesser contrast between the colors. As you go from the lighter side to the darker side, or darker side to the larger side. Is that clear?
Yes.
Okay. So please, the size of your pixels and the pixel density, that is going to what will determine your spatial resolution. The number of bits which is going to be directly proportional to the number of shades of gray, which is going to give you as okay, I'll be directly proportional to your grayscale, will determine your contrast resolution. But the greater your grayscale, the lesser is going to be the contrast. So greater grayscale, lesser contrast. Smaller grayscale, greater contrast. And the greatest contrast was if you had a grayscale which was bistable, where you only had the possibility of two colors, black and white. No shades of gray. Did you guys get that?
Yes.
Okay. Good. Now just read a little bit on these 2 pages here, 44 and 46. Clear? Okay. And when we come back, it's okay, we can just okay talk a bit about it's okay how to calculate the numbers of shades of gray. Is that clear? Okay. So I see you guys back in, should we say it's okay, 10:35? Is that fair? Okay, guys, have fun tonight. Their relations to pixel density versus pixel size and its effect upon spatial resolution. Okay, contrast resolution, number of bits per pixel.
I have a question.
Yeah, my dear, go ahead.
So spatial resolution is basically just like how detailed an image is?
You can put it that way, yes.
Okay, thank you.
Okay, but my dear, the determining factor is going to be your pixel density. Okay, which is going to be inversely proportional to your pixel size. Clear? Okay, so the more pixels you'll be able to fit into a square inch of your image is because your pixel size is smaller. Okay, okay, and that says okay. Now, if you take a picture taken by us, okay, that digital camera that I bought almost 20 years ago, with okay, yes, 6 or 3 kilopixels. Okay, that could mean as okay, be as okay, the number of pixels per square inch of an image. And compare that to a picture taken of the same thing by as okay, a camera of today, which can be as okay, 24 megapixels. Whatever megapixels means. Millions of pixels, okay, 24 million pixels per square inch. Okay, and put those side by side, you could say that, okay, yes, the one taken with today's camera is going to be as okay, be more detailed than, okay, yes, that picture taken 20 plus years ago. Okay. But this, okay. So to begin with, you can say as okay, spatial resolution is mainly going to be determined by your pixel density, which is going to be inversely related to your pixel size. Okay. So pixel size and density is okay, will relate to your spatial resolution. Now your contrast resolution, my dear, is just how many bits are we able to fit into a pixel. And what that number of bits per pixel will determine is how many colors or how many shades is it that each pixel will be able to accommodate. Okay, where the lowest number of bits that you could have per pixel was 1 bit. Okay, and of course that's okay, there's no upper limit. Okay, there will be, you can say it's okay, no upper limit. Did you guys get that? Okay.
Yeah, so then all we need to know is that a word equals 2 bytes as well. Will we need to know anything else about what a word means?
No, that's just, you can say it's okay, general, that's okay. You can, as I said earlier, it's okay, computer science or programming 101. No, it doesn't really matter. It's okay. Any program that you, it's okay, or it's okay, a course or whatever, a textbook that you may pick up on computer science, okay, the introduction mainly, it's okay, will tell you, it's okay, things like this. Okay. But you can go on into your computer files and see. Okay, it doesn't really matter what kind of file that is, whether that is a picture, whether that is okay as a Word document, whether that's an Excel sheet, whatever it is going to have okay as a certain size, right? Okay, so you may see as okay kilobytes, megabytes, gigabytes, so on and so. Probably not okay. Okay, but when your computer comes with okay as so and so and so many gigabytes of memory, that tells you okay how much data you'll be able to store on it. Okay, now just keep in mind that okay as that byte is going to be 8 bits, and giga is just going to be as okay a billion. Mega is going to be 1,000,000. Clear? Okay. Did that make sense? Okay. So if you made, for instance, that says okay, files of 1 megabyte each, you'll be able to store yes, okay, 1,000 files onto 1 gigabyte. Okay. Don't go that extreme because what may happen is that okay, as your computer may shut down. There's going to be as okay a certain limit that they will tell you that okay, well listen, that you have to just okay leave empty on your memory. Otherwise, it's okay. You may try to start your computer, and okay, yes, it won't turn on because it needs certain amount of portion of your memory to remain vacant just for the system to just okay be able to get up and run each time. Did that make sense? Okay. But any digital file that you have is going to have okay as a certain size, and it's going to yes okay be written in your library. That's okay. If you go and look at, let me just, we can go and say details. Okay, guys, let me just see. Yeah. Now this is, guys, this is mainly as okay what, okay, as a file or folder on my computer may look like. Or not may look like, it actually is. So as okay, we just have as okay the names of different files. Okay. We have the date, and okay, here you have the, that's okay, file format or type. So you can see, okay, some of these are pictures, some are GIFs. It's mainly, okay, just also pictures. But it's okay, here you see size. 78 KB, 75 KB, 35 KB, 1620 KB. So what does the KB stands for? Those are going to be your kilobytes. Yeah, okay, and of course, yes, okay, either if it's a big file, a big picture, it will occupy more space. Okay, likewise, yes, okay, if that picture is going to be more detailed with a greater, yes, okay, what we'll call resolution or spatial resolution and or, yes, okay, contrast resolution because it has a greater grayscale on that picture or image. Of course, that's okay, will occupy more space. Did you guys get that? Okay, but for you guys to remember, bits, well, okay, a basic unit of computer data, meaning it's okay, derived from the term binary digit. Why binary? Because computer data is made up of series of zeros and ones. Now, hopefully that's okay. If I want to open a picture, for instance, I would like to see a picture that's okay appear on my screen. Okay, I don't want to see as okay skulls and knives and bowls and crazy letters of okay as any weird language to be as okay displayed on my screen, because that may mean that okay as my system was not able to as okay reconvert that digital data back into an analog format, which would have been the file that I will open. So that's mainly as okay what happens with your when okay as a virus infects your computer. And you may go, oh, what the happened? Yeah. But bits for our concern, yes, okay, basic computer data, or yes, okay, binary digit makes up the term bit. What's a binary digit? Mean it's okay, just ones and zeros. 8 bits, like 000011111. These are 8 bits. They make up 1 byte. So 1,000 of these, or whatever pattern, makes up 1 KB, which is going to be 1,000 or kilo byte. Did you guys get that?
Yes.
Yeah.
Okay, guys. Now for us, because okay, what we mainly say is okay, because yes, okay, number of bits per pixel was going to yes, okay, because it's okay, determine the number of shades of gray. Or let's say okay, shades per pixel. Now the formula is 2 raised to the power n. Where the number n here, well, n here mainly is going to be as okay the number of bits per pixel. So we can take any number, but 2 is going to be multiplied by that number. So if you say it's okay, 2 raised to the power 1. What does that mean? That means that's okay, just means or equals, or that's okay, it's going to practically mean, sorry, that 2 is multiplied by 1. Okay, now here it's okay, that one is simple because okay, that's just going to be 2. So for instance, okay, a pixel only had 1 bit. You could only have 2 shades. And what we know is that those 2 shades mainly as okay would just be only black and white. And that was what we called bistable. Now the next number of bits that we can have can be 2. Clear? Okay. Now 2 raised to the power 2 mainly just means 2 multiplied by 2. So in that case, okay, we get a total of 4 sheets per pixel. Of course, that's okay. One is going to be black, one is going to be white, and then we can say, okay, just in between, yes, okay, 2 possible shades of gray. Now it gets a little bit more, that's okay, when we say, it's okay, 2 raised to the power 3. Now these are mainly, yes, okay, the number of bits. So what does mean, yes, okay, that each pixel has 3 bits. Okay, but that does, okay, this 2 raised to the power 3 here, guys, that does not mean 2 multiplied by 3. By mainly means that, okay, you multiply 2 by itself 3 times. So where we actually end up is 2 times 2 is 4 times 2 is 8. We actually, that's okay, we'll have up to 8 shades per pixel. If a pixel has up to 3 bits. Likewise, guys, if we go and say it's okay, 2 raised to the power 4. Now, as I just said earlier, it's okay, 2 raised to the power 4 does not mean, or it's not going to mean 2 multiplied by 4 because that becomes 8. That's what we just got here. Okay, so that's not what it means. It actually means that you multiply 2 by itself 4 times. So what you get in that case, 2 times 2 is 4, times 2 is 8, times 2 is 16 shades. Or let's say it's up to 16 shades. Did that make sense? And that mainly is okay, just is going to be as okay. What if you, for instance, okay, had 5 sheets, 6 sheets, or 7 sheets? Well, they're going to be as okay by 2 bits per pixel or 3 bits per pixel. All these here and up to 8 shades will be 3 bits. Likewise, okay, any number greater than 8 shades that we could say as okay will be. What about 9 shades, 10 shades, 11 shades, 12 shades, 13, 14, and 15 shades per pixel? 3 bits would have been too big for that because 3 bits could only give us up to 8 shades. So any number greater than 8 up to 16 shades will be as okay by 4 bits. So if a picture is asked, or you asked about What if a picture has, okay, yes, 12 shades? How many bits would that need? Well, okay, you still need 4 because bits per pixel, because 3 is too less, because that can only give you up to 8 shades. Did that make sense? The upper limit for 4 bits is, well, okay, it can give you 16 shades. What if you have, well, yes, okay, 17 shades, that's going to be, yes, okay, 2 raised to the power 5. But this doesn't mean this 2 raised to the power 5 doesn't mean 2 multiplied by 5. That is wrong, but it's going to be 2 times 2 times 2 times 2 times 2, 5 times. 1, 2, 3, 4, 5. And then you just go. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So 5 bits can give you up to, okay, 32 shades per pixel. Up to 32. Where 16 shades was, okay, as was going to be, as okay, you could achieve that by 4 bits. But any number that is greater than 16 shades, up to 32 shades, will require at least 5 bits per pixel. Did that make sense?
Yes.
Okay, right. So just as we know that, okay, is any number raised to the power, that raised to the power number mainly means that, okay, you multiply that number by itself this many times. Okay, so you can see, yes, okay, as the number of bits per pixel, as the number gets greater and greater and greater, yes, okay, the difference between the minimum and maximum is going to, yes, okay, explode. Did that make sense? Just if you look on your, it's okay, there is a small list in your book. Okay, yeah, 25 is okay, 30, you can go to 6. Okay, now 6 bits is going to be as okay, 64. So the difference between 32 and 64 is really great, right? You go as okay, 7. That's going to be as okay, 120 something, 128 sheets. Of course, that's okay. The difference between 128 and 64 is even greater. Okay. And when you go and say, okay, what if we have 10 bits? Well, okay, yes, up to, yes, okay, 1,024 sheets per pixel. Okay. But, the greater the number of pixels, the greater the number of bits per pixel, that will determine your, or that will set your contrast resolution. Okay, but please keep in mind, guys, the greater the contrast resolution is because you have a greater number of shades of gray, which means that you have a greater grayscale, which will, as okay, reduce so that you will have a lesser contrast as you go from darker to brighter. Clear? If you guys recall, yes, okay, the grayscales that I showed you guys yesterday. Oops. Right, guys? So here is okay again. Just two different gray scales. Where we now could say that, okay, yes, this was A, and this one here was B. Clear? Okay. Now what we see here is, okay, as we go from A, point A, from darker to, or from lighter to darker, from darker to lighter, it's okay. A is okay, that has a greater sorry, that's a greater grayscale.
Bless you.
Thank you, dear. That's a greater grayscale, right? Compared to B, which is a smaller grayscale. Yeah, okay. Where we could say, okay, if we used grayscale A, yes, okay, we will have a better contrast resolution. Whereas for B, yes, okay, we will have a poor contrast resolution. Clear? Okay. But what we see is that, okay, as we go in grayscale A down the scale, what we find is that there's going to be a lesser contrast between the neighboring shades compared to here we see a greater contrast between the shades as we go from lighter to darker. Or for instance, or for instance, okay, did anybody decided to paint their room a different color? Good. So what have you chosen to do, Teresa?
3 of the walls are a tan, and there's an accent wall that's a sage green.
Okay, but let's try to stick to one color.
No.
No. Okay, one type of color. Let's put it this way. Okay, let's say as okay, you want to go for green. Okay, now you go and yes, okay, ask the people at Home Depot, I want to, yes, okay, look at some greens. Clear? Okay, now they may throw a big elbow in your and say, well, okay, from page 23 to, yes, okay, 223 are the 200 different shades of green that you have, that we have. Clear? Okay, and you're going to see, and you're going to look at those 200 shades and say, okay, this is too much. So you say, okay, thank you very much, and you walk out. You walk out to another store and say, well, okay, I'm looking for some green colors. And they say, okay, throw a pretty similar album in your and say, well, okay, from page 23 to page 83 are our shades of green. Now here is okay, you just have only 60 shades. Yeah. Okay. But what you actually find is okay, compared to the previous store where they had 200 shades, there's going to be okay, a greater contrast in this store here between, yes, okay, shade of gray as you go from the lighter side to the gray darker side. That's okay. Did that make sense? Clear? Okay. Okay. So what is that the word contrast means? Difference. So the smaller your scale, the greater will be the difference. Because from one side to the other side, you have to start from white and go to black. Did that make sense? That's always going to be as okay, the two extremes of your grayscale. But even as okay, in any color, you can have different hues. You can have okay, super light green. And on the other side, you can have okay, super dark, super dark green. That light green may be so light that it looks like white. That dark green may even be so dark that it pretty much okay resembles black. Okay, so when okay, but yes, okay, they will still be characterized as greens, or blues, or reds, or yellows, or pinks, whichever. Did that make sense? Okay, so the greater your scale, the greater will be your varieties of colors within that scale. Which mainly is okay, well, and if you have a greater varieties of colors to yes, okay, use, you can actually yes, okay, make a better contrast resolution. Does that make sense? That's why it's okay, black and white pictures says okay. It's hard to just okay really determine what color jacket was it that person was wearing. Because let's say it's okay, brown could have been as okay, that color of gray that you see there. Or even as okay, green. So on, so on, so on, so on, so on. Did that make sense? Okay. So my guys, in regular ultrasound, what is that we are actually okay, going to be dealing with? Black and white and XYZ number of shades of gray. Okay, that's your regular B mode. B is okay, brightness, but also boring to look at. Clear? Any questions, guys? Or you can say as okay, the greater the grayscale, the greater is going to be as okay, the number of bits per pixels. And that's going to just okay, improve our contrast resolution. Because even yes, okay, within, let's say it's okay, reds, for instance. Okay. If I say, okay, draw a picture of a red rose, I only give you, okay, one type of red. Okay. You will not be able to just, okay, put that effect of, let's say, okay, shades and so on, so in that. Okay. But if I give you, okay, let's say, okay, 4 or 5 different shades of red and say, okay, here, now try to draw that same rose. I'll paint that same, a picture of that same rose again. Well, okay. You actually, that's okay, will be able to just, okay, improve that picture quality because now you have more shades to deal with. So you can say, okay, this was a little darker shot because that was okay as where we didn't have much light falling on that, okay, that structure. Let's say, so, okay, we are painting the picture of a rose. This area is going to still be right, it's still going to be red, but it's going to be a lighter red because that was exposed to more light. So you actually are able to give that third dimensional. Yes, okay. Did that make sense? Okay. Oh, yes, okay, guys. If you look at the two pictures on 15.6, same picture taken of the same guy, just with two different grayscales. Now, what you see is, let's say it's okay on picture Y. Maybe a little bit. Okay. Good. But what do you see? A lot of shades here. Okay, and maybe it's okay, just black. Okay, even here it's okay, just black. Where here it is more detailed. Okay, here is okay, the color of his cap. Here maybe it's okay, just pretty plain black. Where here is okay, we see some black, but then we also see some shades of gray. So here, yes, okay, this is a poor contrast resolution. Where here, this is a better contrast resolution. Even if you look at his shirt. Now here's okay, the shirt is made as okay, just plain white. It okay has the gray stripes. Yes, okay, the shirt is still white, but yes, okay, you still see that okay, within that shirt there are going to be areas due to just okay, the folds and so on and so on, so that may appear slightly grayish. That's because okay, we have those shades of gray available. Okay, or that's going to give us a better contrast resolution. Did that make sense? Any questions, guys? Okay. And as far as, okay, yes, calculating the number of shades of gray, you will see as, okay, a big bunch of questions about that. Okay. So please remember this formula here. 2 raised to the power n. The n is going to be the number of bits per pixel. Okay, you say 2 raised to the power 1. It's just going to be 2. You go 2 raised to the power 2. Sorry. Is going to be 2 times 2, which then become 4. You go 2 raised to the power, 3 is going to be 2 times 2 times 2, or the cube, which becomes 8. You go 4 is going to be 2 times 2 times 2 times 2, which becomes 16, and so on. Did that make sense? So 2 shades was bistable. Anything more than 2 shapes, 3 or 4, you had to have 2 bits. Anything greater than 4, you have to have 3 bits. Anything between 4 to 8 shades. So 5, 6, and 7 still would need 3 bits. If you had anything greater than 8 shades to 16 shades, that's okay, that will require 4 bits. And so on. Did you guys get that?
Yes.
But please keep in mind, guys. So because it's okay, greater number of bits, or I guess the number of bits per pixel will determine what we call the contrast resolution. Okay, where we say lesser number of bits will cause this contrast resolution here to be poor. The greater number of bits will cause this contrast resolution here to be good. Okay, but likewise, guys, we can also say that, okay, yes, the lesser number of bits that lead to, yes, okay, to a greater contrast. And vice versa. Lower contrast. This greater contrast here, because of lesser number of bits, is going to, yes, okay, also mean that we have a smaller grayscale. And on the opposite side, greater number of bits per pixel is going to, yes, okay, give us a greater grayscale. That makes sense? So the things written in blue all goes together. The things written in, that's okay, purple, if that's what you want to call this color here, is all goes together. Any questions? Nope. Okay, guys. Now, do you guys have any questions about pre and post processing?
No.
Okay, so the main, yes, okay, pre and post processing that we may come back to and talk about today is going to be read and write magnification. Okay. Now, what was pre-processing? Any processing of an image before that was stored in the memory. That was called pre-processing. Yeah, okay. Whereas post-processing, any processing of a image in our case here is okay, or data after it has been stored in a memory. Clear? Okay. One thing that I said yesterday is that pre-processing is not reversible, whereas post-processing is reversible. Did you guys get that?
Yep.
Good. Now in post-processing, okay, what we most likely as okay may do is, well, okay, yes, anything on either as okay, an image that already has been saved, or processing on a frozen image. Because what happens when the image is frozen is okay, the memory saves it. Or it is being stored in your memory. Okay. Now let me just see, because yesterday is okay. I found some pictures. Very good. Hey guys, please look here. Here. So this is pretty much okay. That's not it's the right picture. Okay. Sorry. That was the wrong picture. Probably this one here. So here we go. That's more like it. Yeah. So this is okay. That's what a console of your keyboard, or yes, okay, of your ultrasound systems may look like. Right? Okay. And what do we see here? This button. No, it may not be clear, but it's okay. Where it says down here is freeze. So whenever you turn this button, and okay, yes, it turns. And the writing here is okay, this light here is okay, it turns green. That may mean that okay, as whatever image you have on your screen is now frozen. Did that make sense?
Yes.
Okay. And when your image is frozen, then it doesn't really matter whether you take off your probe or your transducer, because image has been saved on your screen or frozen. So even if you move the transducer, that is not going to affect your image because it is frozen. Frozen in time and space. Yep. Okay. So any processing that you may do on this image here, after that will be considered as post-processing. Clear? Okay. Any processing that you did before freezing the image will be pre-processing. Okay. Now, what mainly as okay came in pre-processing, as we said yesterday, was most of your receiver functions. Because as I did in your SOK paragraph 15.7, as we just can reproduce that. And guys, please, this thing is going to get handy for your next chapter. So we said, okay, this was the transducer. We said that was always going to be analog. And the fact that would be important for analog is that, it was going to be limitless. Well, what did we have? We said here, that we had an analog to digital scan converter. Now, in between this, somewhere here is in the diagram, if you want to put it, that's going to be where your receiver is. And what was it that we could do by the receiver? Compensation, we could do compression, we could even do amplification. Things like that, right? Okay. Even things that are going to be done here as a biosystem, but before it's stored or can convert from an analog into a digital format, like as fill-in interpolation and so on. So things that we will come across later on in this chapter here are still going to be as pre-processing. Okay. But ultimately, as this data here is was going to be stored in the memory. So anything that happened here was pre-processed. Anything that happened to your data after being stored in the memory and be displayed in a display. If your display, for instance, was a digital display or a flat screen, or even if it was, it's reconverted by a digital to analog scan converter, mainly is to be displayed on a analog display or retrieved in an analog format, like a printout or something like that. Okay. Had to be first converted from an analog or from digital back into analog format data. Okay, but all this, which way you go, is post-processing. Did you guys get that? Well, mainly yes, guys, yes. To show yes, how is it that you actually will be able to yes, freeze an image is by yes, this knob here on your system. That is actually just going to freeze the image that you have. Okay. And now you have an image, yes, pretty much frozen. And then we can start doing what we may refer to as as read magnification. Whereas anything is that may as have been done before as that image was frozen or had been write magnification. Now we will take that up after Lynch. Okay. But just think of it. You have a picture that was this small. And you want to enlarge it into yes, okay, 1.5 square inch image to an 8 by 10 or 16 by 20 or 20 by 24. There is going to be magnification. Clear? Okay. But how is that going to, yes, okay, affect your spatial resolution? Is going to be, yes, okay, the next question. So take your lunch break. Reread on your spatial resolution. And it's okay, look at a picture in your library, or it's okay in your file that you want, it's okay, magnify. Okay. I'll find a picture that's okay that we can try to, it's okay, magnify on our system here and share it together and see, it's okay, how that may affect the spatial resolution or the quality of the picture. Okay. So it'll be fair that I see you guys back at 12:30. Good. Have fun till then. Okay. And let's go over to, yes, okay, our next topic, which is going to be magnification. And magnification is mainly as okay by what we as okay will refer to as okay, zooming in. Okay. But on a picture as okay, or on image, what happens as a result of magnification or zooming in? We can say okay that the substance or subject viewed is going to appear greater in the image. Or likewise, guys, as I said earlier, you had an image which was a model size picture. Okay. And mainly it's okay converting this wallet size image here into yes, okay, let's say it's okay, 8 by 10. That is going to be yes, okay, a process of magnification. Is that clear?
Yeah.
Yep. Now, guys, first yes, okay, why question is Why would you like to magnify? Let's just go back to us, okay, this picture here. Or image. Where there's, okay, there's a lot of things. Yeah, okay. Now, the reason that you may like to, yes, okay, magnify this image here is mainly, yes, okay, is because in this image, yes, okay, there may be, yes, okay, something that catches your eye that you would like to, yes, okay, take a closer look at, or look at it in greater or better details. Okay, so that area that may catch your eye, or is okay, may is okay be of your interest, is okay, or a book here may is okay, just call to that as the region of interest. Okay, there, okay, on a regular picture, that's okay, you can mainly see that's okay, let's say, as a dot. So what you mainly do by as okay, magnifying it is that you actually, it's okay, what previously it's okay, just look like a dot or like this. Actually, it's okay. You can zoom in on like an object like this and actually see that, okay, this dot here was not just okay, yes, or something like that, but that actually is okay. Details within this, okay, further details. Maybe you see some sac, maybe you see as okay, some fluid at the bottom, etc., etc., etc. Okay, which you couldn't see here mainly because okay, it was just okay, it's a big or smaller dot. Okay, so the primary goal of okay, yes, magnifying an image is mainly as okay to take a closer look on okay, yes, what we refer to as a region of interest. You guys get that. And that's why, yes, okay, you will magnify an image. Or as we mainly can see as okay, you will zoom. Did you guys get that?
Yes.
Good. Now, guys, just on your keyboard, because the question is, okay, is how is it that you may zoom? And let's just, okay, let's take a closer look at this fellow here. Okay. So this is your B mode. No problem about that. This is, okay, that is your depth knob. And right here, you see this fellow here now, okay, it may not be clear mainly because, okay, I enlarged this picture and okay, as the resolution. But what is going to be written here is zoom. And mainly, guys, okay, when you turn that clockwise, that's when you actually, okay, zoom in. Or we actually can say zooming in is going to mainly mean that you magnify. You magnify into an area of your image. Of course, yes, okay, that area can be, yes, okay, scrolled up or down, at that area that you see that can be scrolled up and down by your mouse. Whereas, okay, on the other hand, okay, if you turn this knob here out anti-clockwise, that's going to mean, yes, okay, that you actually, yes, okay, zoom out. And maybe that's okay, undo the magnification. So once you have done, once you have looked at that structure or region of interest, okay, maybe you even yes, okay, save that image as well. Okay. But yes, okay, what you mainly is okay, down just will do is okay, yes, zoom out again. Clear? That makes sense?
Yes.
Okay. So here, yes, okay, this is pretty much okay, yes, where you, yes, okay, will find the knob. Okay. We can see that, okay, yes, on our image or on our screen. Well, okay, this is what's where this is our screen. We can say it's okay, we have a sector shape image. Let's say that, okay, yes, there's a structure here that catches your attention. Clear, okay? Now what you mean is, okay, just want to, yes, okay, you want to take a closer look on this one here. So it's okay, you will actually just, okay, start to magnify. Clear, okay? Now this is still going to, oops, shit, sorry. The size of your screen does not change. Neither does the size of your whole image that you have change. Okay, but it's okay when we actually, it's okay, zoom in on this area here. There is now going to, it's okay, appear, and you actually will see that this, which was just this size, now it's okay, becomes this big, for instance. Clear? Okay. Okay. Now what you may see is that, okay, as you zoom in, okay, yes, you may, as okay, the zooming window, yes, okay, may get into this area here. And that's why I say it's okay, you can always move the window up by help of, okay, yes, navigating, yes, okay, with your mouse. Okay. And what you actually, yes, okay, will see here on the side as you zoom in, or as you start zooming in, is okay. Oh, that's it. It's okay. Let's do it this way. It's okay. Your whole picture as it was over here. But it's okay. The area is okay into which is okay. You zoomed in. That actually is okay. Going to be highlighted. So if you saw that, okay, as your region of interest, or as okay, the structure that you actually wanted to see was up here. Okay, you can always move this window up by, you say, your mouse, or yes, okay, move it down, whichever. Did that make sense? But now all of a sudden, yes, okay, what on your original image made as okay, just look like okay as a smaller dot. Okay, actually is okay. You can have take a closer look at it. Did that make any sense?
Yes.
Good, good guys. Now, as far as your magnification is concerned, or looking at or enlarging is okay an area of interest, magnification is concerned, yes, okay, we have two types of magnification that we can do. And I know that your book, yes, okay, explain in the other way around, but I'm going to go with this way and say right magnification first. And just to try to make it even simpler, we can say, okay, the right magnification, that is going to be an example of what we say is okay, pre-processing. Did you guys get that?
Yeah.
Good. And what we further can say about right magnification, which is an example of pre-processing, we also said, okay, yes, that this was not reversible, which may mean can't be undone. Once done, it can't be undone. Did you guys get that?
Yep.
Good. Now an example of wide magnification, which is pre-processing. This dude here, or any camera. Okay. Okay. Now, let's say that, okay, you are a sport photographer taking pictures of sport events. Is that clear? Okay. Now you are sitting somewhere else, okay, by the sidelines in the stadium, and you're like, okay, your primary goal was to take close-ups of the players or so and so. Did you guys get that? But then, okay, as one of your fellow photographers come and tell you that, okay, yes, anybody have a favorite celebrity? Okay, I'm not going to pass any comments on your celebrity. Okay, give me a name.
Justin Bieber.
Justin Bieber. Okay, always something, right? Okay, so yes, okay. Caitlin is being told that, okay, Justin Bieber is somewhere in the crowd. Okay. It may be directed at, okay, he is sitting in the crowd somewhere over there. Okay. Now, what Caitlin may be doing is, okay, zoom in. Or it's okay, look at that area where it's okay, suppose the Justin Bieber is sitting. And zoom in and are actually able to just, okay, capture or see Justin Bieber in her camera lens. Clear? Okay. So what did you do here? You zoomed in on Justin Bieber and then you clicked. Did you get that, my dear? Okay. This was a kind of read magnification, where you zoomed in on your region of interest, in this case here called Justin Bieber, and then you capture the picture. Or as okay, in the computer sense, or as okay, in the ultrasound sense, will say, saved it. So once it gets saved, where does it get saved, my dear? When something gets saved, where will it get saved?
Storage?
What would be another word for storage? The computer's memory, right? Did that make sense? But you mainly as okay, zooming in before saving is right magnification. And of course, that's okay. Once that is saved, then it can't be undone because okay, yes, the picture has always been taken, right? Did you guys get that? Clear? Okay. So mainly as okay, you zooming in first and then clicking is right magnification, which will be pre-processing. Because, okay, what are you actually doing? You are magnifying before saving. Did that make any sense? For once, yes, okay, you click, yes, okay, picture taken. Okay, whether that was a picture of the whole stadium or yes, okay, Justin Bieber himself. Justin Bieber, Paris Hilton, Kim Kardashian, whoever. Did you get that? Good. So that was right magnification. Did you guys get that?
Yes.
Good. Now some of you will say, well, okay, how in the blue would I know whether yes, okay, an image has been saved or not? Now, first of all, yes, okay, there's going to be two ways. But let me just show you guys this picture here. Where are you guys? Sorry. Zoom session. Can you guys see this?
Yep.
Good. Not very interesting to look at, but okay, my dear, this is the reality. Clear? Okay. So I hope that everybody can agree upon that, okay, yes, this here is okay, it's your image. Clear? Okay. Now, if you save this image here, what you actually will see, or the way that you actually is okay will know that it is now saved, is that this image is okay will appear down here. So that's going to be as okay your saved images. Magnified or not magnified? Frozen or not frozen? Did you guys get that?
Yeah.
Good. Now your question probably as okay will be that, okay, Mike, we know how to yes, okay, save a program or a file or a document on our computer, right? Right, okay. But how do we do it here? So again, yes, okay, let's go back and look onto your console. Okay, guys, we're going to do a new share. Here we go. Can you guys see this console here?
Yeah. The
And
keyboard.
just so you guys are not completely as okay disoriented. Well, okay, this one here is your B as in bingo mode. This one here is okay, that was your depth. Yesterday I showed you, or even it's okay, today I show you it's okay, this was the button by which it's okay, you could freeze an image. Right now it's okay, freeze is not active because the light is yellow. Okay, it's only going to be as okay when it turns green that it would be on. Okay, but here it's okay, we have not frozen our image because it's okay, we were doing what we call right magnification. But you still want to save an image that you had on your screen. And that's going to be this blob here. Key one. This is mainly as okay, you are safe.
Is that the same on all systems or just the ones that we use?
Now,
At school.
most systems, that's okay, there will be as okay a button that says P1, which will be safe.
Okay.
Yeah, okay. Some of you may as okay be eager to say, well, what about P2? What about P3? What about P4? HNMet or Hakuna Matata. Clear? Okay. So if at any point, yes, okay, you come across, yes, okay, an image, you haven't frozen it yet, but you might have zoomed in because, yes, okay, you see your area of interest. And you say, okay, this is a good picture of my area of interest. Let me just save it without it being frozen. Click on P1. And what you actually is, okay, then will see is that image that we just had, yes, okay, will be saved down here. Did that make sense? Magnified or not magnified, that's a total different thing. Did you guys get that? So sometimes, yes, okay, you may log on to the machine, it turns on, the monitor appears, and what you mainly see on that strip at the bottom of the screen, sorry, since we have it now, yes, okay, it may be filled with pictures. No matter. You can actually just, okay, scroll through, yes, okay, those pictures, yes, okay, by me, yes, okay, touching this key here. Occasionally, yes, okay, what you may be required to do is delete the whole thing because, yes, okay, the memory is somehow filled up. Okay, so if your memory is filled up, yes, okay, what would that mean? That you won't be able to, yes, okay, save your files. Did that make sense? Okay. But does anybody have any questions about write magnification yet?
No.
Okay. Let's just go on to our next type of magnification. Now, again, Caitlin, you were told that Justin Bieber was somewhere in the what you want to call the crowd, right? Good. Now you are not able to zoom in and capture as okay a picture of just Justin Bieber, which mainly means as okay you are not able to do read magnification, no, write magnification. Okay, okay, but you're not going to give up. Clear? Okay. So what we had was, okay, let's go here. Okay. What we had was, let's say, it's okay, we had a picture taken of a crowd. A whole bunch of people. Okay. You say, well, okay, at least, okay, yes, I took a picture of the crowd and the area where JB might be seated. So you go home, you put that picture on your computer. You saved it, right? Where did you save it? On your computer's memory, right? Right there?
Right.
Good. And now you, yes, okay, start zooming in. And let's say, yes, okay, that's Justin Bieber, he was seated in this chair here. And you may, that's okay, by, okay, yes, enlarging the picture says Okay, here we got you. So when this area here is okay, is zoomed in, and you now see it. Like this. And you may see Justin Bieber. But since that's okay, that was okay as magnification on an image that just okay already was saved. Or you as okay, even if it was already as okay on a frozen image. That is going to be read magnification. Yeah, okay. Did that make sense?
Yes.
Good. Now, my dear, unfortunately, yes, okay. I don't have a picture of Justin Bieber in a crowd. But let's just take any picture. Now, what you guys will see is, and that's going to be okay important, that in in wide magnification, your pixel density of okay as the original picture versus as okay that of your region of interest does not change. Because why? My dear, you zoomed in on Justin Bieber before clicking. Okay, so that close up that you got of Justin Bieber means okay by zooming in on him before it's okay taking the original picture, it's still going to be as okay a 24 megapixel picture. So when you take that home, okay, yes, you can print it out. It's going to be as okay a picture with a good spatial resolution because it is still a 24 megapixel picture. Okay, so the pixel size is not going to be affected by wide magnification. It's going to be opposite or the way around if you took a picture of the crowd and then, yes, okay, came home, uploaded that picture on your computer, and then, yes, okay, try to zoom in and see, yes, okay, where was it at? Justin Bieber or whosoever it is was. Clear? Okay. So let's just look here. Now, anybody like oceans? Good. What do you mainly find in oceans? Ocean, seas, lakes, something like that.
Fish.
Fish, okay. We're not going underwater, my dear.
Dolphins.
We are not going underwater, dear.
They
I know
jump.
dolphins come up like this. Okay, peace be with that.
Waves.
Good. Here we go, guys. A picture of a sea view. And you guys see this?
Yeah.
Good. Now, guys, this is already a picture that has been captured. Did you guys get that?
Yep.
Good. But does it look nice? Or let's say, yes, okay, can you still, yes, okay, clearly see, yes, okay, what you have on the picture? Well, okay, yes. We have a boat, 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 we have a boat. We have buildings over here, so okay, we have a bridge. Things like that, right? Did you guys get that? Okay.
Yes.
But maybe, yes, okay, we were told that, okay, yes, on this board here, yes, okay, that was where, yes, okay, just to be off. So this becomes, yes, okay, our area of interest. But Sky saying this picture is okay, already has been clicked, or because it's okay, already have been saved. Now, the kind of magnification that we're going to be doing now is going to be read magnification, which is a example of post-processing. But let's just assume that this board here is okay, is our region of interest. Yeah, okay. And just look carefully what happens. Now, what you guys may see is that the image that okay, yes, previously as okay was of a good spatial resolution. Why? Because of a greater spatial density. Due to, yes, okay, a relatively, yes, okay, smaller pixel size on our unzoomed in image. Actually, yes, okay, now looks like more like bigger boxes. And just so you guys can get an idea of, yes, okay, you see this little area that I mean, yes, okay, marked. That is 4 pixels. Yeah, okay. So what you see is that, okay, yes, the pixel size increased. Well, okay, you say, okay, this thing here doesn't look anything like a board. It could have been anything. It could have been a tower in this ocean. It could have been anything. Forget about that's okay, seeing is okay, just computer sitting on this board here. Okay. But what we just did was an example of read magnification. Okay, so what's going to happen to you is okay, read magnification is that the pixel density of the region of interest in the original image compared to yes, okay, to the zoomed in image is going to yes, okay, decrease due to yes, okay, the increasing pixel size. And that's going to yes, okay, cause that your spatial resolution is going to be degraded. But this yes, okay, what I just did here was read magnification. Did you guys get that?
Yeah.
Good. Whereas, whoops, shit, that's probably true. Whereas, if somebody told you before this picture here was clicked, that okay, yes, the person that you are looking for or trying to capture a picture on was on this boat here. What you could do was zoom in on this board here and then take the picture. Where okay, yes, your board was okay, where that picture was going to be as okay, the whole board like this. And of course, that's okay, you can see as okay that Mr. JB was sitting here. And it was going to appear clear. Did you guys get that? Okay, so it's all a matter of whether it's okay, picture is saved before you zoom or whether it is not saved before you zoom. Or we can say frozen. Clear? Okay. Because, okay, once you, yes, okay, freeze the frame, yes, okay, it gets stored to the memory. Clear? Okay, so once it is stored to the memory, yes, okay, because it is frozen and you zoom in on it, there will be read magnification, which is an example of post-processing. Now, once you zoom in and then, yes, okay, save, what's going to happen is going to be that zoomed in image that will be saved to the library or archive or memory, as you call it. But if you don't want to, well, okay, you don't have to. Clear? Okay. So, yes, okay. Whosoever was, who had zoomed in on, okay, yes, whatsoever, okay, it's only going to be seen once they click. Here. Now, a cheat to remember which is which is pre-processing, which is post-processing. Now, guys, when it comes to reading and writing, what needs to be done first? Listen to the question. When it comes to reading and writing, what should be done first?
Right.
Writing. Okay. If I ask you to read a book which hasn't been written yet, would you be able to do so? Yeah, okay. So write magnification is pre-processing because first you gotta write, then you'll be able to read, right? Clear? Okay. If this book hasn't been written yet, how can you read it? Clear? Okay. So write magnification, dear guys, is an example of pre-processing, and that can't be reversed or undone. Clear? Okay. Practically speaking, right magnification is done on an unfrozen image, an image that hasn't been frozen yet. Did that make sense? Whereas once you freeze your frame, and do magnification on that, that's going to be read magnification. Did you guys get that? Any questions? Yeah, okay. So that's okay. What we just did with our pictures. Oh, yes, okay. The picture that already is okay was saved. Retrieved from the memory. That was mean it's okay. How we do read magnification. Okay. Where right magnification would have been as okay had I zoomed in on okay as something before taking the picture. The boat, the bridge, or any of the buildings, so on, so on, so. But what you also saw as we as okay zoomed in on this already saved pictures or saved picture, that the pixel size increased. Clear? Okay. Now, had this been taken with a camera that had okay as a lesser pixel density, let's say it's okay just 2,000 pixels versus just okay 20,000 megapixels or 20 megapixels. To begin with, yes, okay, the pixel size will be greater. And okay, yes, that's why okay, as a camera with a low pixel density. Okay, yes. Once you start magnifying that picture beyond a certain size, it's okay, that picture is going to look more like bigger boxes because the size of the pixels increase. Is that clear? And when the size of your pixel increases, that's fine, Kristen. We just wanted. um, as your size of the pixel, yes, okay, increases, how is that going to do? That's going to, yes, okay, degrade your spatial resolution. Because you end up having less pixels per square inch. Did you guys get that? Anybody who still didn't get it? Okay, guys. So that's okay. On your sheet, what do we see? We see zoom, right? You guys have your sheets, practical sheet? Yeah, okay. So hopefully that's okay now, not live, but that's okay. On the picture, I show you guys which knob to maneuver with to zoom in and zoom out. Yeah, okay. Below that is freeze. This is a knob by which, yes, okay, you may freeze an image. Yeah, okay. And pretty much, okay, all what happens, yes, okay, once you freeze most of your system knobs, also, yes, okay, going to freeze, but it's okay. You can make it okay, but when you freeze, that's mean going to be, it's okay. This is going to turn green. Okay. How do you mean it's okay by pressing it? How do you unfreeze it? Press it again. And the light is going to go from green to yellow. Yeah, okay. Whereas the button right on top of freeze, which is P1, is safe. Clear? Okay. Now, somebody asked me earlier, are all systems going to be like this? Not necessarily. In some system, yes, okay, you might find your freeze button here on the screen. You may find, yes, okay, your P1s and so on, so on, so. So that's mainly because, okay, well, okay, yes, the functions on your keyboard or the size of your keyboard is going to be smaller. Okay. And you actually, yes, okay, have systems where, yes, okay, your whole system is going to be, yes, okay, the size of a regular laptop. Okay, where you then can see as okay, a lot of the functions that we might have had knobs here actually as okay will come on the touchscreen system. A touchscreen, touchscreen, yes. Okay. But don't worry, guys. Okay, yes, they will always be labeled. Okay, so if you get okay, yes, okay, you end up as okay using a new system, your main job first will be yes, okay, where do I find yes, okay, the necessity functions? Where are they? How do I access them? Okay. So how is your preparation going?
It's going.
It's going. Is it crawling on elbows and knees, or is it walking?
Somewhere in between, maybe.
In between, okay. Now, any questions from your previous chapters? Any point, any relationship, any vector, parameter, typical value, its unit, blah, 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 that you want me to elaborate on. Yes, guys.
As far as like spatial resolution,
Mhm.
do we really need to know about that for the midterm?
Now, my dear, okay, and that's why I said, even those axial resolution, lateral resolution, and elevation resolution together could also all be referred to as, okay, as spatial resolutions.
Okay.
But with that said, my dear, since we, yes, okay, from now on, when we talk spatial resolution, what's going to determine that will be the it's okay, pixel density. Clear, okay, where your pixel density mainly is okay will increase if the line density is increased. So mainly it says, okay, along each scan line, that's going to be as okay the number of pixels that you will have in an image. So let's say it's okay, that's if this here is okay, was your image. And these here is okay, were your pulses. But what these pulses here also are going to is okay, determine is okay as your pixels. Yeah, okay. Did that make sense?
Yep.
Good. So whether you say yes, okay, line density or pixel density, well, okay, yes. It may just come down to yes, okay, somehow the same. Okay. Although yes, okay, specifically when we said line density, it was mainly as okay, number of pulses per degree angle of your image or scan. Clear? Okay. which is more as okay for sector shaped images. Okay, where when we say as okay, pixel density that's going to be as okay, how many pixels per square inch of your image. Okay, but yes, okay, it's still going to be as okay related to the number of pulses. So the more pulses you have, the more pixels will you have in a square inch. Did that make sense? Okay.
Yeah.
Now that increased number of pulses, what did that do? That, okay, has improved your, what we previously called EXA resolution, but now we can refer to it as spatial resolution. Right? Good. Okay.
But up until, so like for the midterm though, just we're
No, no,
gonna,
no, no, no. Don't worry about that.
okay,
Don't
so
worry
we're
about the spatial.
worrying about
No,
the
no.
individual, but
Just remember that, okay, as your spatial resolutions could just, okay, together be referring to as, okay, axial resolution, lateral resolution, and elevational resolution.
right, so we need to know them individually and not as the whole, basically. Okay, that's all I was asking.
Why? Because, okay, they are still resolutions in terms of space. Anything is, okay, dependent upon your area upon which you're looking at. Okay, and that's why it's okay, all those three resolutions were measured by a unit of distance, centimeter, millimeter. Clear? Okay. But, where the resolution would be good, where your resolution would be good if the numerical value of that resolution was lesser or just equal to the distance between the two structures or between the structures. Did that make sense?
Yes.
Okay. And that's where you will have to know is, okay, what is the numerical value for each of the resolutions? Axial resolution was half your spatial pulse length. So if your spatial pulse length is 1 millimeter, half of that is going to be half a millimeter, right? Okay. Now you will have a good axial resolution then if the distance between, yes, okay, two reflectors, one in front, one in back, or one shallow and one deep, was at least half a millimeter apart. If they were lesser than a millimeter or half a millimeter apart, then that will give you a poor axial resolution. Did you get that, dear?
Yes.
Good. For your lateral resolution, I don't mean that's okay, just looking at two structures which were side by side. The word lateral actually is okay, mean pertaining to the side. Clear? Okay. So lateral resolution, now what was going to determine, what was going to be the numerical for your lateral resolution? The width of your beam, which we know constantly changes. In the near zone, your beam gets narrow until it reaches its narrowest point, which is the focus, and then it spreads out in the far zone. Did that make sense? So once, yes, okay, the diameter of the beam, or let's say, okay, the width of the beam is either just equal or lesser than the distance between two structures which are side by side to one another, you will have that will give you a good lateral resolution. But, if in an area the diameter of the beam is greater than the distance between two objects which are placed side by side, then that will lead to a poor lateral resolution. Did that make sense?
Yep.
Likewise for your elevation resolution. Or yes, okay, what they just call yes, okay, slice thickness. Right, okay. But again, it's okay. Here is not going to be side by side, but top to bottom. Above or below. Related again is okay to the height of the beam. So again, it's okay here. The numerical value for your elevation resolution is going to be the height of the beam. Okay. So as long as that is lesser than two structures which are above and below, yes, okay, where the beam runs, you will have a good elevation resolution. Whereas, okay, the diameter of your beam from top to bottom was greater than the distance between the two structures, which are on top and above, or it's okay, above and below, then you will have a poor elevational resolution. Clear? Okay. Now I remember no, after record, but okay, yes, when I was in med school, there used to be this market, a shopping plaza, small shopping plaza, but like okay, core up area, and me and my friend, yes, okay, every time we went to town, not to shop, just do window shopping. But we was okay. Our tradition was just okay. Take a few trips through that market, and there was one day in one of the shops there used to be this guy as okay, pretty tall, okay, almost 7 feet or something, 7 feet plus tall. And wherever he used to walk, he looked like okay, used to look at us like you know that's killer looked like what the hell are you guys doing here, right? Okay. And I told him my friend told us, okay, okay, what if he gets into a fight with us? Because okay, he was so tall that okay, yes, we had to jump. Even to be able to just okay, try to be able to just okay, hit him on the jaw or something like that, okay, or punch him in the face. I said, okay, we probably not going to be able to just okay, punch him in the face. But the best way to just okay, mainly knock him out is just grab him and push him towards the door because he is so tall that okay, yes, he had just okay bend down to just okay come out through the door. So it's okay, bam, okay, he's just going to be knocked up against the wall as we push him. So I say that's the only way that we actually just okay may be able to fight him. But in 7 years, okay, he never said anything. But he just give you this look. You go, okay, well, this guy is okay. He is pissed. Okay, but that would have been okay as a bad elevational resolution. Okay, right. Too tall of a guy just okay walk through the door. Okay, bad lateral resolution is okay. Too chubby to walk through just okay. Yeah, narrow door. Any questions? Now, Christian, if that thing, that's okay, standing on 4 behind you gets on shoes, how tall does he get?
Well over 6 foot.
Yeah. Right, okay. So that's okay. And he may not be able to walk straight through that door, or just on shoes, right? So that's okay. Bad elevation resolution. You can put it that way. Okay. Okay, guys. Anything else? But then your temporal resolution will just be as okay in terms of time. Okay. In terms of time. You say, okay, what just happened a few seconds ago versus now? If yes, okay, we're able to just okay, give okay as a good account on those, it's okay. Even just okay, that was a good temporal resolution. Okay, but that requires that we have a high frame rate with a low chi frame. What will give us a low chi frame is if the number of pulses per frame was less and or if our depth was less. Did that make sense? And these were two as okay things that we could adjust. But just remember, it's okay, high frame rate, good temporal resolution, low frame rate, poor temporal resolution. And then you can go and say, okay, what gives you a low frame rate? A greater chi frame. What was a greater chi frame? Mainly, okay, something that was going to take or make your system take a longer time to create one frame. Did that make sense? And what is one frame? One picture, one click. Because, okay, we can click on that, freeze on that frame, and that'll be it. And then we can magnify it or whatsoever. Okay. But mainly because it's okay, a good temporal resolution may as okay mainly be determined by less number of pulses per frame. Clear? Okay. Which mainly is okay. Will mean less pulses. That's okay. Lesser pulses will yes okay degrade our axial resolution. It will degrade our lateral resolution. Did that make any sense? So that's how you yes okay tie the things together. Now anything. Okay, guys, now please do not confuse things such as PRP with period. Because things that may be determined by your PRP is not determined by your period. Okay? And vice versa. So don't fall for those traps. I'm telling you of the kind of landmines that I may be throwing up on questions. Yeah. Anything else?
Mike, are we gonna have study days this week or no?
Yeah, what day is it today? Wednesday?
Today's Tuesday.
Tuesday, okay. Tomorrow we're done with this chapter here. So Wednesday, so you can say Thursday, Friday, we can have review or revision or whatever you want to call it. Clear, okay. So after, yes, okay, your midterm, yes, okay, or the day after your midterm, yes, okay, we can get on to chapter 16. But it's okay, this chapter will be done tomorrow. There's not much more to fill in police and all that in here. Yeah, okay. Maybe it's okay, just 2, 3, yes, okay, important topics. Okay. Anything else? Nope.
No.
No, guys. Okay. Then which transducer will have a better exit resolution? Shorter pulse duration or longer pulse duration?
Shorter?
Huh?
Shorter?
Shorter pulse duration, because shorter pulse duration is just an indirect way of saying it's okay, shorter pulse length. Okay. Common factor was number of cycles, but if the period is shorter, the wavelength is shorter. Okay. High frequency has dash penetration. High frequency transducers has dash penetration.
Can you repeat that?
High frequency transducer has dash penetration.
Shallower.
Or lower penetration, right? Okay. Primarily due to greater attenuation. Right, okay. Good. Now, how will you correct an image which is too bright? You had an image that was too bright. How will you correct that?
Decrease the power.
Decrease your power up roar, transducer up roar. Dun, 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 dun. Clear, okay. Good. What will be a way of minimizing the production of noise? Minimize the production of noise. Yes, guys. Mainly because of a high signal to noise ratio. High signal to noise ratio. Okay, guys, that will be increase your power output. Okay. Now I just had to, yes, okay. If you go to page 219, the last paragraph. Last paragraph, second sentence. As the sonographer increases the power output, the signal to noise ratio also increases. It may mean you produce more signal and less noise. Because power output has a high signal to noise ratio. And that's how we actually minimize the production of noise. Right? Good. But if noise still is being produced because we had to amplify the image to a certain brightness, then how do we get rid of that noise? How do we get rid of that noise? Reject. Oops. Over reject. Eliminating low intensity signals, which was noise. That's why I say it's okay. A buzzing mosquito is not a Metallica concert, right? The full-blown, yes, okay, sound system, right? But still is okay. Continuous unwanted sound, especially as okay if you want to go to sleep. Okay, guys. I guess you haven't got to chapter 14 yet. That's fine. Okay, guys, see you guys tomorrow, and we is okay. Well, now please make sure that you has okay for tomorrow. Just make sure that you know your frequency tuning, right? Oh, dynamic frequency tuning. And relation of frequency to penetration. You'll find those. Okay, I just talked about those. But if you remember, yes, okay, your frequency or dynamic frequency tuning, I said something because, and then you should have seen something. Good. And just look into your Webster's dictionary or whatever dictionary you have and look at the word compounding. Yeah. Yeah. But have fun. Enjoy the day. Enjoy the sun. Or whatever it is. And see you guys tomorrow. Okay?
See you
See you
tomorrow.
tomorrow.
Okay,
Thank
guys.
you.
Have fun. Bye-bye.